Okay, good morning, everybody. Bonjour. And it's been a real privilege and a pleasure to speak to you this morning. And let me start by thanking Anna for the very kind invitation and to Shulin in quarantine for actually looking after all the organizational aspects of it. And it's been a wonderful morning to start off with interacting with the young students at IIP. And thank you very much for making the time for that as well. So today we will talk briefly on an aspect which I've spent a bit of time working on, the giant radio galaxies. And at the outset, I'd like to say that feel free to ask me questions in between. There's no issue. And we will finish in about an hour, right? An hour's time. Yeah. So including question time. So feel free to ask and we'll leave some time for questions at the end as well. And I'll keep it tab on the time. Okay. So what you see on the image over here is today the largest single structure, a giant radio galaxy, about 7 megaparsec. It's about 6.34 or so when it is not deprojected. When it is projected size, and when you deproject it, it's about 7 megaparsec, is what Martin Oy and his collaborators have estimated. It's at a redshift of about 0.9, and the supermassive black hole they've estimated is about 6.7 into 10 to the power of 11 solar masses. In this picture, what you see is the size of the Milky Way. So you can see this is, over 200 times the size of the Milky Way from end to end. This is again a pictorial representation of the Milky Way blown up 10 times. So these are the largest single structures in the universe, and they are the products of evolution of radio galaxies. We are born young. They are born with very small sizes, and over billions of years, they grow to these huge dimensions. They're the largest single structures in the universe, carrying energy, momentum, and magnetic fields. And they pose a lot of interesting astrophysical questions, including the generation and transport of energy over such large scales, whether instabilities, how do they remain stable over distances of about several megaparsec in length. And the generation of energy in these objects is believed to be due to accretion onto a supermassive black hole, whose mass you can see over here for this particular object. So accretion is a process by which these energies are fueled. So if you look at the total energy in them, they're indeed very large, over 10 to the power of 60 ergs or so. And this is the largest one which is known. It was discovered from observations with a low frequency array, the European telescope, starting from Netherlands. And we will have a look at the properties of these objects. And as far as a definition is concerned, when you talk about radio galaxies, they're born young, they keep growing, and there's a whole range of sizes from parsec scales, which are buried within the confines of the host galaxy, to the largest structures over here. There's no discontinuity in the sizes. And as a working definition, today, most workers take 700 kiloparsec as the size of a giant radio galaxy. Initially, when it started off, okay, well, let me see. I think the animation got stuck. Okay. One second. Yeah. Okay. Okay. Yeah. Sorry. Okay. Initially, the existence of this class of sources, which are very large in their size, was brought to our attention way back in 1974. And the two objects which Tony Willis and others, Richard Strom, and Wilson wrote a paper on in Nature, was 3C236, and this remained the largest source for a long time, as we should just see, with a size of 4.59 megaparsec compared to what we just saw, 7 megaparsec, and this is slightly smaller, about 1.4 megaparsec or so. An aspect which we will visit today is that this is about 4.59 megaparsec, but right in the center of this source is also a compact radio source with a steep spectrum, which is associated with this galaxy. And when you observe this source with high resolution, you get a mini kind of double inside this source. So this is an example of a source which you'll also discuss in a bit more length later, where there seems to be more than one cycle of jet activity. The jets have started off, lived for several millions of years, then for some reason it switched off, and then it restarted again. So these objects are called rejuvenated radio galaxies or restarted radio galaxies. And where there are two pairs of lobes, these were referred to as the double radio galaxies, and we shall talk a little bit more about them later. So as you can see over here, that this is a field which has grown quite a bit over the years, and that is what we shall see. But progress in the initial years was slow. This is an example of a giant radio galaxy which Yerky Machalski and we found from images made with the GMRT, which Anna talked to you about a short while ago, and also the Effelsberg telescope. And this was the largest, larger than 3C236, discovered after many years. You can see 1974 was that paper, and this was 2008. So nearly 34 years later, one found an object which was larger than 3C236, which was about 4.6 megaparsecs. When we model this source in terms of its evolution, we can understand it in terms of a powerful jet evolving in a low-density environment and with a ballistic propagation of powerful jets over there, forming these very bright hotspots at the outer edges. So as the beams propagate outwards, these are the size regions of interaction of the relativistic beams which are squirting out from the active galactic nucleus. When we talk about radio sources, Bernie Fanaroff and Julia Riley at Cambridge, a long time ago, 1974 to be precise, classified the broad structure of radio galaxies into two categories, which are today known by their names as Fanaroff-Riley Class 1 and Class 2. This is a Class 2 source which has prominent hotspots at the outer edges, regions where the beams collide with the surrounding medium as it snowplows its way through. These tend to be of higher luminosity. Unlike the Fanaroff-Riley Class 1 sources, which I'll show you examples in a short while, where the jets dissipate a lot of energy as it goes, it doesn't form these kind of bright hotspots at the outer edges and just form diffuse plumes of emission. The radio emission which you see over there is due to synchrotron emission, ultra-relativistic particles gyrating in a magnetic field, so that if you had a 10 GeV electron gyrating in a field of 10 microgauss, you would get radiation at about 20 centimeters or so. Okay? Now let's move on a little further, just to show you how it has evolved over time. And this slide over here shows you the way the number of giant radio sources has evolved. And I've just given a few select references. And you can see the most dramatic increase in numbers have happened in recent years. And that is largely because of the LOFAR telescope. And why has LOFAR made such a big difference? Because once you want to detect these large structures, they're often, the hotspots are fine, but they're also, very weak, as you saw from the first image over there. They have a steep radio spectrum, and because of a steep radio spectrum, it is something which you can see or detect more easily at lower frequencies. So LOFAR operating at 144 megahertz has been an ideal instrument, particularly with the kind of sensitivity it has had. So I've just given a few select examples over here of surveys which have tried to detect giant radio sources and identify them over the years. But as you can see, it is only in the last few years that it has really made a difference. So Martin Oey, from the LOFAR DR2, identified over 2,000 of them. And Pratik Dabade, actually from an earlier release of LOFAR data, had found about 239 of them. And most recently, just a couple of years ago, Mossart et al., they applied machine learning algorithms to try and identify giant radio sources and came up with about nearly 11,500 of these. So unless actually these machine learning algorithms are not perfect and there are issues, and unless one physically actually checks them, one does not really know. Heinz Andenach, who has been working on giant radio sources, he's tried to maintain a catalog by looking at each one individually, and he has about 7,000 as well. But you can see that the numbers have grown dramatically in the last few years. When my former student Ishwar Chandra and I, we looked at the sample way back in 1999, by looking at the entire literature and also making our own observations, we could identify only 53 of these, 48 associated with galaxies and 5 with quasars, and the situation has really changed dramatically in terms of the numbers. But has the physical questions changed? Perhaps not as much as one would have liked, and I'll try and look at that as well. Now, here is a picture just to give you a scale that we're talking about. Right at the bottom, we can see Cygnus A, which is 120 kiloparsecs. And that was one of the first radio galaxies to be identified, one of the early ones with an optical object. Then you have Hercules A. And when I talk about Fanneroff-Rayleigh class 1 sources, you can see this object, Hercules A. It doesn't have these bright hotspots in the edges. We will meet Hercules A again in a short while. And just diffuse plumes of emission with the jets being highly dissipative. And these are generally of lower luminosity, although from lower observations and papers by Beatrice Mingo and collaborators, we know that the situation is a bit more complex today. Whereas these ones with prominent hotspots, this is 3C236, and this is the one which we had found. This is Alcyonius, which is about 5 megaparsecs, which again came from the LOFAR group before they reported the 7 megaparsec source. So you can see these in various stages of evolution, but this is also pretty large compared to the most compact sources that we are familiar with. We follow the evolution of these sources on a luminosity size diagram. All the background things which you see are different samples taken from LOFAR as well as well-known samples like the 3CRR, the Third Cambridge Survey. And these are the evolutionary tracks of sources with different jet powers. The 3CR sources being the most luminous they are of the highest jet powers, and as you go to low luminosity sources, they are of smaller powers. So this is jet powers of 10 to the power of 35, 36, etc., till 10 to the power of 40 watts, evolving in a loose group, in a small group, with a M500 radius of 10 to the power of 13 solar masses and a temperature of 1 kilo electron volt. So the diagram looks very sort of, it looks like a mess. There's no obvious correlation, but it just shows you the kind of different jet powers in which sources evolve, and the giant radio sources are the most evolved of these objects, starting from pretty young sources. When I talk about more compact sources, these are the ones which are really the baby ones. They are buried right within the central regions of these active galaxies. These are the youngest objects, and they're not in kiloparsec. They're in a few kiloparsec, parsec level, or a couple of hundred parsec level. They look like mini doubles, but sometimes you also get more complex structures like 3C48 over here, where the jet has been completely disrupted by interacting with the external environment. Whether all of these young sources or little baby sources evolve into the giant ones is a moot point, because there are too many of them to explain the numbers of larger radio sources. So ideas have been floating around that not all of them make it to large sizes. Some may be just sort of sputtering, have activities for a short while, remain as small sources and don't go to large sizes. Some of them may be confined to small dimensions by a dense intergalactic medium, and this is the current understanding, that there is a mixture of different kinds, and when you estimate their ages, they are rather young. I'll talk to you a little later about how we estimate ages from spectra, but for some of these young sources, you can actually measure the motion of the objects with VLBI measurements, and you can actually go back and say when it started off, and some are as young as a few hundred years as well. So these are the really baby radio sources. And when you observe sources with high resolution, you can also find evidence of interaction. For example, this is one source which Bill Cotton and some of us have mapped together. And this is interacting with a cloud over here. The jet is bent. It has a high rotation measure and a bit of depolarization over here as well. And I've shown the spectra over here of these sources. These are the most compact ones, have their spectra which turns over, and it's a combination of both synchrotron self-absorption as well as free absorption by the dense gas in the nuclear regions of these objects. These are the youngest objects that we know. The higher the frequency at which they turn over, the more compact the source is buried within the nuclear regions. So this is just to give you a perspective or where the giant radio sources come from. So our focus will be almost entirely on the giant radio sources that we talk about today, which are more than 700 kiloparsec in the projected lengths that we see. Just to reinforce the Fedorov-Riley class 1 and 2, this is the class 1 objects which I talked about. You can see the jets are highly dissipative over here. They are not as well collimated as in the higher luminosity sources. They do not form intense beams. They're believed to be of lower Mach numbers, entrain material, and dissipate their energy as they go forward, whereas these are more well collimated and deposit most of their energies at the edges where they're interacting with the interstellar or intergalactic external medium. These are believed to have higher Mach numbers compared to these and are carrying more energy from the central region over here. There's a new class of sources where there is no extended emission at all, just a nucleus called FR0, but we will not deal with them today. Evolutionary tracks which I showed you. So this is Tao An and Willem Bahn. They were trying to talk of different kinds of evolutionary tracks for the FR1 class 1 and FR1 class 2 sources. I will just introduce one little concept over here, is that you can see that the jet over here is completely one-sided, whereas the jet over here on a large scale is two-sided. And that is believed to be due to the effects of relativistic motion of the jets. So when a jet is coming towards you, relativistic effects result in Doppler boosting of the jet which is approaching you and reduction in the brightness or flux density of the jet as it is going away from you. And that depends on the inclination angle as well as the velocity of the jet. So these sources have lower velocities. These are both, and this is a galaxy as well, and larger angle of inclination, whereas this is a quasar, which is believed to be at a smaller angle to the line of sight and also moving at higher velocity. So the relativistic beaming effects are significant for the jet, particularly for the nuclear jets it would be. Whereas you do see the outer lobes because as they're plowing their way through the interstellar medium, the velocities are really slowed down compared to the velocity of the jet, so that the relativistic effects are minimal, and you see the external lobes, although energy supply appears to be one-sided. In the kind of schemes that we talked about today, that the apparent diversity of active galactic nuclei, or at least some classes of active galactic nuclei, is because of their orientation towards the line of sight and the effects of relativistic beaming. So we'll meet that a little later as well, but let's sort of move on. And one can ask oneself that these are evolving into large sources, what might they look like when they're really very old and energy supply has stopped? This is one such object. And what you can see over here is not even a peak of emission, but a depression in the emission. In fact, the emission is low over here, very diffuse Wolfley lobes, no jets which are active, although there's a little core which is active. And as I mentioned to you earlier, that the emission is synchrotron emission. And what happens is that when you look at a young radio source, you'd get a straight radio spectrum over here for a young radio source. We will see that in a little while again. But what happens is that the electrons which are giving rise to synchrotron emission, at higher energies of the electrons, they're radiating at a higher frequency. And not only are they radiating at a higher frequency, they're also losing energy much more rapidly. So because of that, you begin to see a steepening of the radio spectrum, as long as your fluxes are accurate, as you go to older and older sources. So this break in the spectrum moves to lower and lower frequencies as the source ages with time. So from the break in the spectrum and an estimate of the magnetic field, you can estimate what is called the spectral age of the source. There are a lot of caveats, but I'll not go into details right now. But this particular source is about 150 million years old. The electrons not only lose energy by radiating synchrotron emission, but they also lose energy due to inverse Compton scattering with the cosmic microwave background. So both the energy losses actually contribute to the steepening of the spectrum, so that it becomes more serious when you go to higher redshift, where the cosmic microwave background energy density increases as 1 plus z to the power of 4. Now, this is an example of what could be a very old radio source. As I mentioned to you earlier, just a short while ago, that the electrons may have such low energy, say Lorentz factors of 1,000 or more, a little bit more, and and the radio emission which is coming out from it at the frequencies which you're observing is so weak that you can barely detect it at radio frequencies. But these electrons with Lorentz factors of about 10 to the power of 4 uh, can inverse Compton scatter photons to very high energies. For example, if you had gigahertz photons at 10 to the power of 9, and then you had 10 to the power of 4, it'll go and scatter into the into the X-ray region of the spectrum. So this looks like a double radio source. It looks very old, okay, and this is an object at a redshift of 1.99. And this is from the Chandra deep field, which Andy Fabian and others found. And they said that this is indeed a very old radio source, which you are picking up in the X-ray region of the spectrum due to inverse Compton scattering, but it is too weak. Therefore, the electrons have lost a lot of energy, and you're not being able to pick up in the radio region of the spectrum. We looked at this with the GMRT many years ago, but did not really sort of see the emission. It's worth having another go with the kind of sensitivities we have today to find out if there is radio emission from there, and then construct better models than what has been done. Besides the spectral ages, which I just mentioned, by looking at how the spectra steepen and the break in the spectrum keeps moving to lower and lower frequencies as the sources age, you can also model the source in terms of the dynamical ages, putting in jet powers, putting in densities of the external medium, and try to see what kind of ages they would lead to sources of such dimensions. And I've just put in again a few references over here. Jerzy Machalski from Jagiellonian University in Poland. He has been doing a lot of these dynamical ages. We just celebrated his 90 years just a few months ago, and he's still quite active, which is wonderful. And if you look at the comparisons of the dynamical and spectral ages, they are sort of, okay, given the uncertainties and the model dependencies of both. But you can see that as you go to larger and larger ages, and this yellow one marks the boundary of giant radio sources, which is greater than about 700 kiloparsecs. And these are typically of 100 to 200 million years, whether you do a dynamical aging or a spectral aging. And the youngest ones, as I just mentioned, if you look at smaller radio sources, the smallest ones, you can measure them kinematically as well. But the other small ones, if you want to do a spectral aging, the spectral steepening would be, in a millimeter region or in the high gigahertz region, so that the ages are smaller than the giant radio sources that we have just seen or just been talking about. Now, what are the reasons for the formation of the giant radio sources? Although the numbers have gone up, there's still a relatively small fraction of the total population of double radio galaxies, what are called dragons, double radio sources associated with active galactic nuclei, a term which was first suggested by Paddy Leahy at Jodrell and it's sort of reasonably widely used these days. And various options have been tried over the years or suggested over the years. And let me keep an eye on the time. Yeah, I'm not doing too badly. Okay. And one idea is that they're in very low density environments. So they meet very little resistance, but there's enough material over there for the beams to interact, deposit energy, form hotspots, or travel outwards. But they're generally a lower density environment compared to, say, a cluster or a group or rich clusters of galaxies. The other aspect is AGNs are extremely powerful. They're powerful radio jets. And because the jets are very powerful, that they've been able to travel these large distances. And the third aspect is what I pointed out right early on in 3C236, that there are multiple cycles of activity. Each one keeps pushing so that you get sources developing into large sizes. We look at the evidence of this, and when Ishwar and I in 1999 compiled a sample and tried to answer that question, the questions have been the same. We have now, say 7 to 11,000 sources, but the answers are still somewhat similar. And we need to probably look at it more theoretically, have more information on the environments of these sources to probably make a major dent rather than just numbers of sources identified from radio observations. So let's first look at the environment. I've just again cited just a few select papers over here, just to show you that the situation is a bit mixed. Many years ago, we looked at one of our students. We looked at a sample of giant radio sources, and as you can see, as you saw probably some of the images, some are symmetric, some are not very symmetric, and we try to ask ourselves the question that if we take the very asymmetric sources, can we show evidence that they're running into some asymmetric medium? Is there a higher density of galaxies on that side? There was only one particular case, the most asymmetric case, where the shorter arm seems to be lying along a filament of galaxies over there. But generally, we found the density of galaxies to be low, so that they are in a low density environment. And Malaraki, Jones, Lakshmi Saripalli, they also tried to say that they grow in less dense environments, but just by counting galaxies. But when Pratik and I, we looked at the overlap of clusters of galaxies with the larger sample of giant radio galaxies, we find that 10 to 20% of them are actually in giant, sorry, are actually in much more dense environments, and that is something which tells you that giant radio sources can also form in environments which are not sparse. It's not a unique requirement that they need to grow only in dense environments. A significant number, I mean, not a huge number, but a significant number are known to also develop in bright cluster galaxies, so they develop in rich environments. And this is Lan and Prochaska. They actually counted satellite galaxies in the environment of these galaxies. And they said that the properties of galaxies around the giant radio sources are similar to those around control samples. So locations of GRGs and the control samples relative to nearby large-scale structures, the filamentary structures of the cosmic web, is also similar. So they surmise that the external galaxy environment are not the primary cause of the large sources. So you can see that the evidence is a bit mixed in terms of the large sources. I think what we need to do as a next step is probably have more information on the gaseous environment around them, possibly from X-ray observations, and try and model them more carefully in terms of seeing how important a role it can play. And the kind of results we have got by counting galaxies, small and large numbers, is a bit mixed. So the answer, but it's fair to say probably that it is not a defining criteria, but may play a role in many of these sources. Now, if you want to look at powerful jets, then one thing one can look at is the black hole masses. Is there a difference in the black hole masses of the two systems? In the shaded part, what you see are the giant radio galaxies, and the blue are a general population of radio galaxies, and the median values are almost identical. But the giant radio galaxies being of less luminosity, so you look at the Eddington ratio or bolometric luminosity divided by the Eddington luminosity, then they're generally lower. So they may be accreting, their accretion may be more inefficient, so radiatively inefficient accretion flow may be operating over there. But the other aspect of black holes which one has to bear in mind is the spin of the black holes. It's not just the mass, but is the spin also playing a role? And long time ago, I think Ari Laur wrote a paper saying that if the black hole mass is greater than about 10 to the power of 9 solar masses, they're all radio loud, they're very active in the radio. If they're lower than about a few times 10 to the power of 7 or 10 to the power of 8, they're generally radio quiet or radio weak, and in between we get a mixture. Again, LOFAR observations, Sabater et al., who have had large samples of both radio and samples which have been well studied in the optical, showed that radioactivity depends strongly not only on the black hole mass, but on the total stellar mass as well. And it shows a much stronger dependence on the stellar mass compared to even the black hole mass. And those are aspects which we need to look at it more carefully. But if you look at the black hole mass itself as a signature of the generation of jet power, then we do not see much of a difference. Spin is something which has been indirectly inferred, but not for a large sample, and that is one thing which we need to look at it more carefully. But I'm not very hopeful that that will lead to many insights, because today when we look at weak galaxies where spin can be inferred or estimated more accurately from X-ray observations, because what happens is that the X-ray lines which you can see, the iron line, which is close to the black hole, there you can go and look at the profile and estimate the spin of the black hole, and you find that even these radio weak sources have radio weak Seyfert galaxies have maximally rotating black holes with a spin factor of about 1. So perhaps it's a combination of both spin and mass, and that is something which you again need to look at, but spin has not been really measured very accurately for a large sample to be able to say much on that right now. Okay, so I'll talk about recurrent activity in a short while, but what I should say over here is that 37. What I should say over here is that almost all the galaxies that we talk about till now, the parent galaxies are elliptical galaxies. Generally, if you look at the large radio galaxies, they are associated with elliptical galaxies. That dichotomy is something which we do not fully understand, but I'll give you some hints on what directions in which people are moving. And only a handful of sources are associated with spiral galaxies. They're literally, less than 24 right now, and it has remained at less than about 6 for a very long period of time. So let me just deal a little bit with spiral galaxies, and then we will move on to recurrent activity and spend some time on how they may also be responsible, or whether they may be responsible for the large sizes that we see. The vast majority, as I said, are associated. And I also mentioned about that. And what is it that leads to these formations with elliptical galaxies rather than spiral galaxies? As I mentioned earlier, that Seyfert et al. Has said it depends very strongly on the mass of the galaxies. So mass function actually for the spiral galaxies goes down pretty rapidly. And people have also speculated that spiral galaxies are gas-rich, and whether actually that affects the evolution or of the ability of the source to go to large dimensions. So recent attempts have been made from the Galaxy Zoo project as well, by Wu et al. and Tate et al. And what we find is that the numbers are still small. It's less than about 24 right now, compared to thousands and thousands of radio galaxies, or hundreds of thousands of radio galaxies. So it's still a small number. But when you find them, they occur throughout the Hubble sequence. These are not all giant radio sources. These are just double lobe radio sources. Even double lobe radio sources are small, and a small fraction of giants, or small fraction of them are giants, very few of them. And when you look at the optical profiles of them, they generally seem to have pseudobulges rather than the classical ones. Classical ones, as you know, are the elliptical galaxies with this random motion all around, and have probably grown by mergers of galaxies, whereas these have grown by more secular processes, gradual accretion. You still see some regular rotation in the bulge of the galaxy, although several have disturbed dust lanes as well. The other interesting thing is that, particularly I'll highlight Gene Tate's work, is that they actually found the largest number, but most of them actually belong to the Fanneroff-Rayleigh class 2 category, with prominent hotspots at the outer edges over here, and not the Fanneroff-Rayleigh class 1 objects. I had mentioned earlier that these tend to be of higher luminosity, but these are often of lower luminosity and yet have that structure. And that is something which has also been coming out a little bit from the LOFAR observations, which Beatrice Mingo and others have published. So the picture is gradually changing. Overall, it is still true that Fanneroff-Rayleigh class 2 sources, which are more luminous, but we see a lot of counterexamples, and there is a significant layer of overlap. When we look at the spectra of these galaxies, they're usually of type 2. They have narrow lines rather than broad lines, as one expects of galaxies, where the broad lines may be hidden by a torus in the canonical model of an active galactic nucleus. But a very small fraction are giant radio galaxies over there. So we'll come to that in a little while again. The other aspect we try to do is that how common are these in narrow-line Seyfert 1 galaxies? What are narrow-line Seyfert 1 galaxies? They are broad lines much broader than the type 2 galaxies, the Seyfert 2 galaxies, but not as broad as the Seyfert 1 galaxies. This is a category which is brought to our attention by Osterbrock and Pogge, Goodrich, others who brought this to our attention. Flux ratio, this is defining complexes, O3 to H beta less than 3. There is strong permitted Fe2 complexes, the steep X-ray spectra, rapid X-ray flux variations. And the interesting thing is that they have low black hole masses. And if you look at their accretion rates, the Eddington rate, they are accreting quite rapidly. And the Eddington luminosity, because of their low black hole mass, is typically about 1.3 to 10 to the power 38 m solar mass of solar mass of the supermassive black hole in terms of solar masses. So you can plug that in and get a number. And the host galaxies are again largely believed to be spiral. So we try to use the latest catalog of these objects, the Sloan Digital DR17 catalog, and try to identify a complete sample of Seyfert 1 galaxies using the criteria set forward earlier, and identify a large sample of both narrow-line Seyfert 1 galaxies by looking at the individual spectra, as you can see, of many objects. This is a project led by Vaidehi Palia. And when we look at these objects, the question that we are asking ourselves, can these form large-scale structures that we are discussing today? Again, the numbers are very small, but we'll just show you how many there are. What you can see, I will not go through each one over here, but you can see that the broadline Seyfert 1s are black histogram, narrowline Seyfert 1s are small, and you can see that this is a significantly smaller black hole mass compared to the broadline Seyferts, which results into a higher Eddington ratio, and redshifts of the two samples are similar. So we try to look at the radio properties of them. In terms of just the radio detection itself, it's very few. We detect only about 3% of them, even slightly smaller than earlier estimates, because we have been able to extend the redshift, and the radio observations have not been sensitive enough for the larger redshifts to pick up more numbers. And among the ones which are detected in the radio, they're about 63% of the narrow-line Seyfert ones, 77% of the broad-line Seyfert ones are radio loud. And by radio loud, what we mean is that the radio flux density divided by the optical flux density has a ratio greater than 10. And this was what was defined by Kellerman, Ken Kellerman and his group, while looking at quasars many years ago, 1989, I think. And then we looked at the radio structures as well as the gamma ray properties of these objects. The gamma rays usually originate from the lobes due to inverse Compton scattering, as well as from jets. And we have been able to identify a few of them, a small fraction of them in gamma rays, suggesting that they do harbor jets. But when you want to look at the radio structures, we really have to go back and look at all the available catalogs and see whether we can identify them. So we find that 34 narrow-line Seyfert 1s have a projected size greater than 100 kiloparsec. And that is a huge change, because before this, there were just very few. Actually, there was just one which was convincing, and there were a couple of others. And there were at least two which were convincing, and a few other candidates. And this has been made possible by using the LOFAR catalog, because you can see over here, the orange contours are the LOFAR surveys over here. And you can see that many of these objects, you'd never see the extended emission with the low frequency emission, because they have steep radio spectra, and not only the steep spectra, but LOFAR with its sensitivity has made significant contributions in understanding of different areas, including the large-scale structures around narrow-line Seyfert 1s and Seyfert galaxies. Here, 4 are giant radio galaxies, including one which is about 4.3 megaparsec long, and 4 are gamma ray emitters as well. And these are small black hole masses. So there has been some argument, I'll probably not go into this, okay? There has been some argument that these small black hole masses, which you're seeing by narrow-line Seyfert 1 galaxies, is because of projection effects. Why is it because of projection effects? Because you're trying to estimate the black hole masses. In nearby galaxies, you can do reverberation mapping, all that. But in these more distant objects and large samples, you try to infer it from the relationships of the black hole masses with the line widths. If the clouds are moving about rapidly, which are giving rise to the broad lines, then they would be moving more rapidly due to the due to the influence of the supermassive black hole. Higher black hole mass will have larger weight. But what people are saying is that are these objects just pointed towards you and the movement is not random but on a plane? Then the velocity in your line of sight will be small. Okay, will be small. And how do you actually go and, then it'll give you a small black hole mass because of geometric effects, and you're inferring, small widths because of the geometry. Now, we try to do that. We try to test it out a little bit with a few sources that we had. It requires further study. But what we try to do is that what is plotted at the bottom is a degree of codominance. Why is the degree of codominance important? Is because the core has a nuclear jets over here. And if it is pointed towards you, its flux density is going to be Doppler boosted. If it's going to be Doppler boosted, it's going to have a more dominant core. And if it has a more dominant core, then it should be at a small angle. So we try to look at black hole masses versus, codominance, and we don't find any correlation. Also, some of the largest sources we have, which we expect to be at large angles associated with galaxies, are also ones with the lower black hole masses. So it doesn't seem to be that projection is playing a major role, but this is a small sample of sources, so one has to look at it more with greater caution. And also, we are trying to get better spectra for some of these sources than from the Sloan Digital Sky Survey to test whether classification is right. Are there weak, broad lines which we have missed in the Sloan survey? That is something which we are also trying to follow up using more sensitive observations. If I plot these sources as these narrow line Seyfert ones on a luminosity size diagram, which we used earlier to study the evolution, they seem to lie in the general region of the more luminous radio galaxies and quasars. These are all radio detected sources with by LOFAR with an AGN. Okay. Now, on the theoretical side, this is an effort which is led by Gaurav Giri, who is now at the Institute of Radio Astronomy in Bologna. He has been trying to use the Pluto code, relativistic MHD simulations, to see that by simulations, what are the powers that you need, what are the physical conditions that you need to produce these giant radio sources. So these are simulations of low jet power and high jet power. The power is given over there. The low jet power corresponds to Fanner-Riley class 1. The high jet power corresponds to Fanner-Riley class 2. And try to follow the evolution of these sources using this Pluto astrophysical code. And he finds that these jets, the low power jets take longer, but they're both able to reach sizes about 3 megaparsecs or so in not unreasonable times, given the ages that we talked about. In fact, his simulations reach these sizes faster than what the spectral and dynamical age estimates are generally done. He's now trying to extend this to 5 megaparsec and even to the largest sources, but the kind of grid size which you need is very computer intensive, and that is what he's doing that, but it's taking a bit of time. So theoretically, by simulations as well as analytical estimates, it is possible, given the right choice of density, and also to keep the jets collimated, where magnetic field plays a very important role, because as the fluid flows, instabilities develop, and you can see in the Fanner-Riley class 1 source, particularly, that a jet is beginning to break up over here, whereas in a FR2 source, it is better collimated and forms a head, the hotspot at the outer edge. But these are interesting in terms of trying to understand from a theoretical perspective. The giant radio sources also occur in clusters of galaxies, as I mentioned, and the cluster environment can also distort these structures tremendously. And this is an example of a wide-angle tailed source, where it is not a collinear structure, but you can see filamentary structures. It's a beautiful image of a wide-angle tailed source made with a Meerkat telescope by Bill Cotton, and we had tried to interpret it and make models of it. And on the lower right, what you can see is just simulations using the Pluto code again, but trying to mimic a cluster environment by rotation to try and explain the kind of ribbons and tails which you see in this wide-angle tail sources. So from a theoretical perspective, by right choice of densities, jet powers, and external environment dynamics, one can understand a lot about the structures. Now, let me see, how am I doing for time? Okay, I have another about 10-12 minutes, so we'll keep the time. But if you have any questions now, or we'll keep it to the end. Anyway, feel free to ask at any time if you like. So as I mentioned earlier, a little while ago, that when you have jets which are coming towards you, their flux density is enhanced. The gamma ray emission is really at the highest frequency end. Today we are talking about radio emission, where the radio photon has an energy of about 100 megahertz, about 10 to the power of minus 7 electron volts. Gamma ray photons, at GeV range, 100 GeV, 10 to the power of 12 electron volts. So we're looking at energy levels which are separated by nearly 20 orders of magnitude and trying to understand these sources. Now, when we look at the gamma ray detections of giant radio sources, there are not too many. And if you look at the gamma ray sky, this is from Jean Bellet's earlier pie diagram from 2023. They have a more recent compilation in 2026. That a bulk of them are blazar candidates or Bielefeld or flat spectrum quasars. Without getting into details of these objects, they are basically sources whose jets are pointed at you and the flux density is getting enhanced, and that is why you detect them. Other extragalactic, galactic are very small, unknown because of the poor resolution of gamma ray observations, where you can't really focus rays as you can do even in the X-ray regime with a bit of luck with the nested mirrors, but you can't do that at gamma ray energies because of the high energies involved. The error circles are large, and a large number of objects which are unassociated. Now, we try to find out about giant radio galaxies. What is the story? Before going to the giant radio galaxies, let me tell you about Centaurus A. Because it is nearby, Centaurus A was also one of the very early radio galaxies to be identified reliably because of its large angular size and nearby, and the optical galaxy is also large. You can see that this is a gamma ray emission map from Fermi at the top and a W map at the bottom. And you can see emission not just from the jet, but from the lobes as well. This has been interpreted to be due to inverse Compton scattering with the cosmic microwave background radiation. And other radio galaxies too have been interpreted in terms of inverse Compton scattering, not only with the cosmic microwave background radiation, but also with the general extragalactic background light and also light from the parent galaxy. So one can try and construct models of detailed spectral energy distributions of these objects, taking all these into account. We first tried to see, by more carefully than what the Fermi group had done, in terms of increasing the number of just galaxies. And then we sort of did that by looking at catalogs, getting better accurate positions of the Fermi sources, and we increased the number to about 150. Then we went a bit further and say, let's see how many of them are giants, and can we find giants over there? So we found about 16 sources, which are giant radio sources and also Fermi gamma ray emitters. And here again, the cores of these are generally stronger than the average population of the cores are over here, than the general population of double radio galaxies. So we believe that there could be a core contribution, but there is also contribution from the lobes via inverse Compton scattering with the different backgrounds, and detailed modeling is something which we are currently doing. And this has also been done by other groups as well. Parsec and Raffaelli, they have modeled Centaurus A in GC6251, which is also a giant radio galaxy. And generally, these giants also has photon indices, which are similar to the general population of radio galaxies, the 149, which we had identified. And the giants are at the end of this luminosity size diagram. But a small fraction, you can see that only 16 of them have been identified so far. So the last topic I will touch upon is the recurrent activity. The doubles, which we talked about a little while ago, right in the beginning. In the case of 3C236, this is a classic example where the core is completely unresolved with the VLA, but with VLBI kind of resolutions, milliarcsecond resolutions, the core is split into a double. Now, how do you identify recurrent activity? We'll spend a few minutes, look at a few examples, and then we will close and look at the supply. So another 10 minutes at the most. Okay. Now, when you see two different pairs of doubles, in the case of the Fanneroff-Riley class 2 sources, it's easy to say that you're seeing two different cycles of activity. But on the other hand, when you see diffuse lobes, what do you do? One way of approaching it is, for example, in the case of Hercules A, this was done by Nick Ghezani and Paddy Leahy, that the younger emission has a much flatter spectrum compared to old plasma, which is over here. So if you do very careful detailed spectral index imaging, you may be able to identify that. The other cases over here, which I pointed out, NGC B0258 plus 35, is where you see a very distinct compact source, well defined in the central source, and very diffuse emission outside it. Maybe I'll skip this for a time being just to minimize time. You can see evidences of relic emission in compact sources also, but there are not too many of them, but these are on small scales, and there are suggestions that these small scales just keep giving out emission periodically and then die off without going to large dimensions. This is one such source, which was mapped by the Chinese group, Wu et al. But this is another interesting aspect which I should mention is what Catherine Blundell, Andy Fabian, and others try to do, is that this is the famous source signacy. The green are the contours, are the X-ray contours, and the grayscale is the radio sort of emission. And what they're trying to say is that the X-ray contours which you're seeing is again due to inverse Compton scattering of radiation from the old population of electrons, not from a new population. The young population is giving you radio emission. The old electron population is giving you X-ray emission due to inverse Compton scattering with the microwave background radiation or general photon field as well. And there are other examples. So this is an interesting way of trying to look at recurrent activity as well. And when you look at X-ray images of clusters of galaxies, you often find holes of emission. And these were the ones which were earlier occupied by the radio-emitting plasma. You find multiple cavities sometimes, and this is another signature of recurrent activity of an active galactic nucleus. The other way which suggests candidates is to look at the spectra, because here you have a very strong low-frequency component, and this was identified from observations with GLEAM, the Australian survey. And this steep low-frequency spectra is believed to be due to an old population of electrons and old cycle of activity. But we need to actually, image them and confirm that it's indeed the case and not due to, some other sources in the field or whatever. But from the spectra, at least you can get an inclination. Now, coming back to models of giants, what we tried to do, this is a project led by Pratik Damade, we looked at a large sample of giants identified from the LOFAR telescope in a given area of the sky and tried to see what fraction of them are actually double-double radio galaxies showing periods of recurrent activity. And that was to try, and one of the objectives was to try and understand, can this be a viable explanation? It appears not, because just about 3% or less than 3% actually show the kind of morphology which is expected. This kind of study has been possible again with the LOFAR survey turning up large samples of galaxies. So you can see that the reasons are still mixed, and we don't have a clear answer. We may have an answer for one or two objects where there are more detailed studies. For the whole population, we do not. You can go and study the physics of individual objects, estimate their ages and sizes. And this is one object which we did many years ago with the GMRT, the images which you saw of the GMRT. You can see young sources, there is no evidence of steepening. The old reddick plasma, you can see evidence of steepening. And from that, you can go and estimate ages, you can estimate duty cycles. And the old plasma is about 50 to 150 million years, whereas the young one is approximately about 2 million years. I'll just go through a few images over here. This of double-double radio galaxies, which are also seen in spiral galaxies called spiral dragons, or spiral double radio galaxies associated with AGN. And sometimes, just in a few cases, you actually see three kinds of structures, three of them, the triple double radio galaxy. This is one which we had found many years ago in 2011, and that was associated with a spiral galaxy. There have been a few more which have thrown up recently. This was one we found just a few years ago, led by Kitish Chavan, an MSc student who was working with us on this. And there have been one very recently sort of reported in 2026, which is in press with the South African telescope, the MIGHTY survey. And right now, almost all the triple radio galaxies are large sources, giant radio galaxies. Maybe it's easier to spot them over there. But although, one has reasonable confidence, but, I still hold my heart in my hands and say that, are we really sure? Because I think we need a bit more theoretical studies of when a jet sort of energy supply switches off, how long does it take for the channel to collapse? If it starts off again, are we going to see the structures like this, which may not be very well defined hotspots, but we have taken it to be examples of recurrent activity? Are they just knots in a jet that is continuous? So these are questions, I think, which require more theoretical work to try and understand whether what we're trying to infer or at least suggest from the observations really holds up. Some work has been done, but I think a lot more needs to be done. Okay, these are results simulations from Walg et al. And I'll close with this last topic, which is that if activity has started off, there must be a fresh supply of gas, you know, and can we find evidence of gas? So what we have done over the years is that, you see, when gas is present, the most common element is hydrogen. And against the compact core component, can you go and detect hydrogen in absorption? So this has only been done for a few objects so far. It needs to be done for more objects. This is the one which I showed you earlier, where the inner lobe is a double, and we found very complex H1 emission, column density of 10 to the power of 20 centimeters per squared. And this has been, this is another example of which we detected with the GMRT. This is an example just recently reported by the Meerkat group. Again, this little thing which you see over here, when you blow it up, it's actually a compact double over here, and this is the large-scale structure. So there seems to be some inkling, some suggestion that you may find more gas in sources which are rejuvenated, but it needs to be followed up for a much larger sample. Searches for carbon monoxide have not been as successful, and that's because these are largely elliptical with very little gas. And I will close with this last slide. We just mentioned some of the one first letter's got cut off, I'm sorry, but this is a galaxy which we imaged with the GMRT. And I mean, it shows several interesting features: symmetric jets, diffuse lobes, not the double radio galaxies, but where a jet is probably processing to establish the structure. So we need to use GRGs or giant radio sources as probes of the IGM, conditions that lead to large structures, conditions in spiral galaxies, and these may be responsible for even contributing to intergalactic magnetic field. And these are issues which are still sort of unresolved in many ways. And observationally, we have made a lot of progress, but I think on the theoretical side also, we need to sort of look at these aspects in a bit more detail. So I'll end with that. Thank you very much for patiently listening.
So it's time for questions.
Hello, thanks for the wonderful talk. I was just wondering, in the context of radio jets, because radio jets are often they require large simulation domains, often also ad hoc prescriptions for non-thermal electrons, and then there's a lot of environmental interaction at play when you set out to model radio jets. How do you sort of tackle these issues while theoretically modeling radio jets?
You're talking about radio galaxies in the environment.
Yeah, in a
feedback processes.
Like in a wider population of black holes, if there's a radio jet within an AGN source.
Okay. Now, one thing is how do you form a jet at all? Okay. The other thing is what does a jet do to the galaxy? Right. So these are two different aspects. One is extraction of energy from the jet. The broad process is accretion of matter. But a detailed physical process of actually extracting energy, one expects that the rotational energy is sort of what you're extracting out, and magnetic fields are playing a very important role. And there were two broad processes which were worked out by Bradford and Yannick and Bradford and Payne. And these are still the two main principal processes by which energy is extracted to form the jet, where you spin up magnetic fields, build up stresses, ejecting material around the direction. But the ultimate source of energy is accretion onto the black hole. And to explain the kind of energies which we see, say even 10 to the power of 46 Earths per second onto a 10 to the power of 8 solar mass black hole, you need just about a couple of solar masses per year kind of thing. So it's not a huge number, but once the jets are out, they can, particularly for the low luminosity, because they're less collimated, they can go and affect the galaxy much more severely than those are a very narrow angle, which interacts less with the whole medium. And these feedback processes are important in terms of the star formation history of the galaxy as well, because once you heat up the gas, it's more difficult to form stars over there because the gas is heated up. But the other aspect of these narrow collimated jets, which Martin Rees talked about many years ago, is that they could actually also compress clouds and lead to bursts of star formation. And observationally, when you look at it, one is called a positive feedback, the other is called a negative feedback. That negative feedback when you inhibit star formation, positive feedback when you enhance star formation. Observationally, both from kinds of jets that we see evidences of both. In fact, the other kind of activity in galaxies where star formation or starburst activity take place, even there we see that there is evidence about negative and positive feedback on the interstellar medium of the host galaxy. So I think it is important to understand, you're asking the right question in terms of it holistically, because in terms of the evolution of the universe as well, these feedback processes are important to fold back into the cosmological evolution models.
Sorry, also the radiation processes that you spoke about, how sometimes a photon starts off as mostly seeded as a synchrotron, and then it gets scattered off along the way, and then you get kind of like X-ray scattering or X-ray emission. And sometimes like there's all sorts of correlations. Like if you think about fundamental planes, it kind of like ties into these quantities together. It ties into radioluminosity and X-ray luminosity and the black hole mass together. And if one were to kind of like model these, it's not trivial to model, because often these correlations suggest a common source within the accretion disk, right? And it becomes harder to model in the context of that.
Yeah, you're absolutely right. I mean, the fundamental plane is telling us something very fundamental about the way galaxies are evolving, and it's important to try and understand and model that. Absolutely.
It's also like not, it's understudied as of yet. Like we don't know what exactly are the physical origins that kind of like further these relations.
We know a little bit, but we need to know more. I mean, for example, fundamental plane is one aspect of it. I mean, today if I look at star-forming galaxies, I find that there is a very strong correlation between the gamma ray emission and the infrared emission.
Mm-hmm.
And that relationship I can understand in terms of gamma rays being generated in explosive events like supernovae, which also leads to, which is the result of intense star formation, which will heat up dust, which will give rise to infrared emission. So if that dominates, you would get a relationship between the gamma ray emission and the infrared emission.
Right.
So some of these relationships in terms of both AGN as well as starburst are sort of understandable, but in terms of detailed theoretical model, because a lot of physics has to get in. For example, even if I have a proton which is being generated, how much of it is within the galaxy, how much of it escapes without interacting?
There's a lot of assumptions to
that is still a large uncertainties in all.
Yeah, exactly.
Absolutely.
Thanks for the talk.
Yeah, thank you very much. Thanks a lot.
Thank you. Other question?
Yeah, Michelle.
As you know, some of us here are working more on the optical side of the AGN. So my question is there any relation between the episodic nuclear activity you see in the radio and variability in the optical? Of course, for BLX, when the jet is directed towards us, you are dominated by the jet in the optical, so you don't see any feature, only continuum.
Yeah.
But in ellipticals, it's the same. AGN are rarely directly seen in AGN, but I'm interested in the few cases you mentioned of these spiral galaxies where you have some lobes in the radio. It would be interesting to have a look at those particular ones to see whether there is a correlation between radio and optical. Have you looked at that somewhere?
Yeah, I mean, let me give you just one or two examples of what you're saying is very important. I mean, particularly, for example, if I look at the gamma ray perspective, because you're looking at really the highest energies over there, okay? And you want to ask yourself, if there is variability, what is the reason and where is it originating from? And one of the radio galaxies associated with elliptical galaxy, which has been monitored more extensively because it is relatively nearby, and also there's a lot of photons, large signal to noise ratio, that you can look at it for long periods of time, and that is M87. Now, M87, what has happened is the Chinese observatory, the high altitude, they have been looking at gamma ray emission almost continuously from 21 to 24, and they find that there is a flare which goes up and then comes down with 1 day and 2 days. Now, earlier flares which were seen, there was one correlation of a flare in the gamma rays with an X-ray flare from one of the knots very close, the HST1 knot. So then you say, okay, this is where it is originating, and I know that this jet is inclined at small angles, and that may be the origin, and try to model it. But subsequent flares, they find that HST1 was quiet. There was, variation right in the nucleus over there. So we find that indirectly there is variation in origins from different areas. Now, in terms of the Chinese flare, because of the short time scale, you can go and infer using the Lorentz factor, correcting for it, what is the length scale over which it has come? Where has it come? And then you find it has come from just a few times the Schwarzschild radius. So, and that is one aspect of it. By tying together variability at different wavebands, you could actually try and put some constraints on what is happening. Now, variability is also can be used to try and constrain whether the emission, for example, at high energies you're seeing, is from an AGN or from a star formation. Because if it is a star formation, supernovae which are going off and giving rise to emission, you don't expect rapid variability. So if you have gamma ray emission even from a star forming galaxy and you see rapid variability, then it is likely to be an AGN. So you can use those constraints, but unfortunately today, actually, in terms of multi-wavelength monitoring over long periods, telescope time is at a premium. Yeah, that is the main challenge actually in terms of trying to, although with whatever data is available. I mean, Fermi is looking at objects continuously. Some of the others mentioned the Chinese observatory is focused on this object, looked at it for quite some time. But such examples are not too many. Sometimes they have dedicated missions, but regular monitoring of large samples is, I mean, of course, the Palomar factory or the Zuki transit factory, I mean, those are generating plots in the optical. But at radio today, we don't have any monitoring at all of, a sample of sources, even at high frequency.
You have used the small sample of spiral galaxies when you have this extended.
Yes. No, it would be interesting to actually get time to monitor that. I mean, one has to try and convince the time allocation committees to give us time to. Yeah, we'll discuss that. Yeah, later. Yeah.
Other question? No, thanks. Oh, sorry.
Here is a question. Yeah.
Question. Okay. Talk. Great talk, by the way.
Thank you very much.
Wanted to ask you, you don't cover much about the magnetic field.
Yes.
Are we learning anything interesting and the distinguishing features of the magnetic field in its large radio galaxies?
A distinguishing feature of magnetic fields in large radio galaxies. I think we are making some headway, but in terms of actually looking at, okay, let me put it this way, is that we are making some progress. I mean, there are two things we want to study. One thing is that we probably want to put constraints on any thermal material in the galaxy from depolarization measurements of the radio emission. You want to look at correlations between depolarization and rotation measure for to infer whether there are fields wrapped around it and what is the kind of thermal plasma which is surrounding the source, and also general propagation or of enriching the magnetic field in the surrounding medium. Okay. And also using these as probes to study what is in between. Now, in terms of general radio galaxies, we have made a lot of progress on studies of individual sources. For large radio galaxies, because they're very large, the depolarization is slow. So you really need the low frequency observations. So I think, with the low far polarization observations, we are making a little bit of progress, but I think we need to do a lot more work on in terms of understanding the properties around these from polarization observations. Because high frequency, there is very little depolarization of these radio sources. Smaller ones, you get depolarization about 20 centimeters or 16 megahertz. But these large sources, they're often pretty strongly polarized till 327 megahertz. So we need really low far kind of measurements. So some progress is being made, but I think the whole picture we do need a lot more work done. Yeah.
Great. Thanks.
So thanks again, the speaker, and
Okay, thanks very much.
thanks very much.